Right now, your entire solar system is drifting through a giant cavity blasted open by dead stars. It stretches over 1,000 light-years across. It is filled with million-degree plasma so thin you could never feel it. And until recently, nobody knew it was there. Scientists call it the local bubble. Roughly 15 supernovae carved it out of the galaxy over the last 14 million years, and everything you have ever known, every planet, every moon, every comet, sits inside this one enormous hollow. The walls of this bubble are still expanding, still pushing gas outward, still igniting the birth of new stars along its surface. Most people picture the solar system floating in calm, empty space. The truth is far stranger, far more violent, and far bigger than anyone imagined. If you enjoy journeys that completely reshape how you see our place in the cosmos, then consider tapping that like and subscribe button. It genuinely helps this channel grow and lets me keep making deep dives like this one. Now, settle in and get yourself comfortable. Let's begin. Close your eyes and picture the solar system. You already know what you see. A bright yellow sun at the center. 8 planets arranged in neat orbits radiating outward like rings on a target. Mercury baking closest to the fire. Venus wrapped in acid clouds. Earth blue and green and impossibly alive. Mars rusting in the cold. Then the gas giants Jupiter and Saturn, massive and banded and ancient. Uranus and Neptune floating in the frozen distance. Maybe you add an asteroid belt between Mars and Jupiter. Maybe you sketch in the Kuiper belt, that icy ring of debris beyond Neptune where Pluto drifts in quiet exile. You draw a circle around the whole arrangement. Outside that circle, you leave nothing. Just blackness. Empty space stretching in every direction until you reach the next star 4 light-years away. That is the picture. That is what every classroom poster, every textbook diagram, every documentary animation has drilled into your mind since childhood. The solar system is a self-contained island, a tidy arrangement of worlds orbiting a single star, surrounded by a vast and featureless void. This picture is wrong, not slightly inaccurate, not outdated by a few percentage points. Fundamentally, structurally, dangerously wrong. And the mistake is not in what it shows. The mistake is in what it leaves out. The emptiness you imagine beyond Neptune, that enormous blank darkness you picture surrounding the solar system, is not empty. It never was. The space between our sun and the nearest stars is filled with material. Not a lot of material by earthly standards. You would never feel it. You would never see it with your naked eyes. But it is there. And it extends in every direction for hundreds of light years, and it has been shaping the conditions inside our solar system for millions of years in ways that most people have never heard of. The solar system is not floating in isolation, it is immersed inside something enormous, something invisible to ordinary perception, something carved out of the galaxy by explosions so powerful they make nuclear weapons look like candle flames. And right now, at this very moment, that larger environment is pressing against the outermost boundary of our sun's influence, flowing through the spaces between our planets, and leaving radioactive fingerprints in the mud at the bottom of Earth's oceans. To understand what our solar system is actually embedded inside, we first need to destroy the illusion that it exists alone. And that means confronting a fact that sounds simple but carries enormous consequences. There is no vacuum between the stars. When you look up at the night sky and see individual points of light separated by darkness, your brain interprets that darkness as emptiness. Nothing between here and there, just distance. But astronomers have known for more than a century that interstellar space is not empty. It is filled with an extremely thin but physically real substance called the interstellar medium. The interstellar medium is the material that exists between star systems throughout the entire Milky Way galaxy. It includes gas, mostly hydrogen and helium, along with trace amounts of heavier elements like carbon, oxygen and iron. It includes dust, tiny grains of silicate and carbon compounds smaller than the width of a human hair, grains so small that millions of them could fit on the head of a pin. It includes charged particles, neutral atoms, molecules ranging from simple hydrogen pairs to complex organic compounds, cosmic rays traveling at nearly the speed of light, and magnetic fields threaded through the entire structure like invisible scaffolding holding everything in place. The densities involved are astonishingly low by any standard humans encounter in daily life. In a typical high-quality laboratory vacuum chamber on Earth, you might achieve a density of around 25 billion molecules per cubic centimetre. That is considered an impressive vacuum, good enough for manufacturing semiconductors and running particle physics experiments. The interstellar medium in a typical region of the galaxy contains roughly half an atom per cubic centimetre. That is 50 billion times emptier than a typical vacuum chamber on Earth. By any intuitive definition, this qualifies as nothing. It is so close to a perfect vacuum that you could fly through it forever and never notice a single particle hitting your spacecraft. Your instruments would strain to detect it. Your senses would register absolute emptiness. Every human instinct would tell you there is nothing here. But the universe does not care about human intuition. And this is where scale performs its most disorienting trick. At cosmic distances, even absurdly low densities add up to staggering quantities. A single cubic centimetre of interstellar space contains almost nothing. But a cubic light-year of interstellar space contains a volume so vast that even half an atom per cubic centimetre, multiplied across that expanse, produces a mass measured in fractions of a solar mass. When you then extend this across the trillions upon trillions of cubic centimetres that fill the space between all stars, stretching across a galaxy 100,000 light-years wide, the total mass becomes enormous. Roughly 10 to 15% of the visible mass in our entire galaxy exists not inside stars, but spread through the interstellar medium between them. Billions of solar masses worth of gas and dust, scattered so thinly that no human sense could ever detect it directly, yet collectively outweighing entire populations of stars. If you could somehow sweep up all the interstellar gas in the Milky Way and compress it to the density of Earth's atmosphere, it would fill a volume vastly larger than our solar system. The material is there. It is real. It has mass and temperature and velocity and chemical composition. It is simply spread so thin across such incomprehensible distances that detecting it requires instruments far beyond the range of human perception. This material is not uniform. It does not spread evenly through the galaxy like a perfectly mixed fog. The interstellar medium is turbulent, dynamic, and structured at every scale astronomers have been able to measure. It contains regions of wildly different temperature, density, and composition existing side by side, sometimes separated by boundaries as sharp as the surface of a lake. Some regions are cold and dense, with temperatures as low as 10 Kelvin, negative 263 degrees Celsius, and densities hundreds or even thousands of times higher than the average. These cold molecular clouds, dark and opaque to visible light, are the birthplaces of new stars. Gravity pulls the dense gas inward, compressing it further, raising the temperature at the core until nuclear fusion ignites and a new sun is born. The Orion Nebula, visible as a faint smudge below Orion's belt, is one of these stellar nurseries, a cold, dense cloud in the process of creating an entire generation of new stars. Other regions of the interstellar medium are blisteringly hot. Superheated to temperatures exceeding 1 million Kelvin by the shockwaves from exploding stars, these zones contain gas so energetic that atoms are stripped of their electrons completely, creating plasma that glows faintly in X-ray wavelengths, invisible to human eyes but detectable by specialized space telescopes. A single supernova explosion can heat the gas within dozens of light years to these extraordinary temperatures, and that heat can persist for millions of years before the gas gradually cools and settles back toward equilibrium. Between the extremes sit warm regions of partially ionized gas at temperatures of several thousand Kelvin, neither hot enough to glow brightly in X-rays nor cold enough to collapse under gravity into new stars. These warm zones make up a substantial fraction of the total volume of the interstellar medium, filling the enormous spaces between the dramatic hot and cold regions. The interstellar medium is a patchwork, a constantly shifting mosaic of hot and cold, dense and sparse, active and quiet zones overlapping and interpenetrating throughout the galaxy. Stars are born from it, live within it, and when they die, they blast their outer layers back into it, enriching the medium with heavy elements forged in their cores. The interstellar medium is not a passive backdrop to the story of stellar evolution. It is the raw material from which stars form and the reservoir into which they return their substance when they perish. It is the circulatory system of the galaxy, cycling matter through generations of stars over billions of years, and the solar system is not separate from this patchwork. It is inside it, right now. It has always been inside it. Every planet you have ever learnt about, every moon, every comet, every grain of dust orbiting our sun, exists within the interstellar medium, the way a fish exists within the ocean. The fish may not think about the water. The water is invisible to the fish's daily concerns. It does not obstruct the fish's view of its surroundings. The fish swims through it without resistance, without awareness, without any sense that it is immersed in a medium that extends far beyond its perception. But the water is there, surrounding the fish completely, pressing against it from every direction, shaping the conditions of its existence in ways the fish never perceives. Remove the water, and the fish dies. Change the water's temperature, its chemistry, its currents, and the fish's entire world transforms. This raises an immediate question. If the solar system is immersed in interstellar material, why do we not notice it? Why does the space around Earth feel so empty? Why do spacecraft not encounter a steady stream of interstellar particles slamming into their hulls? The answer reveals something remarkable about our Sun and the invisible shield it projects into the cosmos. The Sun does not just emit light, it emits a continuous stream of charged particles called the solar wind. Every second, the Sun ejects well over 1 million tons of material outward in all directions at speeds between 300 and 800 kilometers per second. This material consists mostly of protons and electrons, the fundamental components of hydrogen stripped apart by the Sun's intense heat. The solar wind races outward through interplanetary space, past Mercury, past Earth, past Jupiter and Saturn and Neptune, continuing far beyond the orbits of all known planets into the cold outer reaches of the solar system. As this wind flows outward, it inflates a bubble, not a solid bubble with rigid walls, but a region of space dominated by the Sun's magnetic field and charged particles. Scientists call this bubble the heliosphere. Inside the heliosphere, the solar wind reigns supreme. Particles move outward from the Sun. The magnetic field is solar in origin. The environment is shaped primarily by our star's activity and output. Outside the heliosphere, the interstellar medium takes over completely. Particles belong to the galaxy, not the Sun. The magnetic field is interstellar in origin and orientation. The conditions are determined by forces that have nothing to do with our local star, forces shaped by events that occurred millions of years before our solar system even formed. The boundary between these two regimes is real, physical, and measurable. We know this because we have crossed it. Twice. In 2012, NASA's Voyager 1 spacecraft became the first human-made object to leave the heliosphere and enter interstellar space. The probe had been travelling outward since its launch in 1977, and after 35 years of continuous flight, it crossed a boundary, roughly 122 astronomical units from the Sun. 1 astronomical unit is the distance from the Sun to Earth, about 93 million miles. So Voyager 1 crossed into interstellar space at a distance of roughly 11 billion miles from home. Its twin, Voyager 2, followed in 2018, crossing the boundary at a slightly different distance of approximately 119 astronomical units. revealing that the heliosphere's edge is not a perfect sphere, but an irregular surface that shifts in response to changing pressures from both sides. What the Voyagers detected at this crossing was dramatic and unmistakable. The density of charged particles from the solar wind dropped sharply, plummeting to near zero. The density of particles from the interstellar medium spiked upward by a factor of roughly 40. The magnetic field changed direction, rotating away from the Sun's magnetic orientation and aligning instead with the galactic magnetic field threading through the local interstellar environment. The plasma wave instrument aboard Voyager 1 detected oscillations in the surrounding plasma that allowed scientists to directly measure the interstellar medium's density for the first time in history. Roughly 0.08 of an electron per cubic centimeter, consistent with predictions for the specific region of the interstellar medium our solar system currently occupies. The data was unambiguous. For the first time, a human-built instrument had directly tasted the interstellar medium and confirmed it was real. After 3.5 decades of flight, covering 11 billion miles of empty space, the spacecraft had finally reached something. It had passed through the heliopause, the outermost boundary of the Sun's direct influence, and entered the ocean of interstellar material that had been pressing against this boundary for the entire 4.5 billion year history of our solar system. Here is where the familiar picture of the solar system begins to collapse entirely. Most people, when they think about the solar system at all, think about the planets. The outermost planet, Neptune, orbits at roughly 30 astronomical units from the Sun. That is about 2.8 billion miles. Everything inside that orbit, the planets, the asteroid belt, the comets and moons and spacecraft, fits within a region roughly 8 light hours across. Light leaving the Sun takes about 4 hours to reach Neptune. A beam fired in the opposite direction takes another 4 hours. The entire planetary solar system, every world humanity has ever studied up close, every landscape ever photographed by a robotic probe, spans 8 light hours from edge to edge. The heliosphere extends much farther, roughly 100 to 150 astronomical units in the direction the Sun is travelling through space. The nose of the bubble, and perhaps 200 to 300 astronomical units in the tail, stretching behind us where the solar wind is dragged backward by the interstellar flow. That gives the heliosphere a rough total extent of perhaps 300 to 400 astronomical units in its longest dimension. In light travel time, that works out to around 2 light days. The heliosphere is several hundred times wider than Neptune's orbit. That sounds enormous until you compare it to what lies beyond. The nearest star to our Sun, Proxima Centauri, sits 4.24 light-years away. Convert that to astronomical units, and you get roughly 268,000. The heliosphere, the entire zone where our Sun holds sway over its environment, extends a few hundred astronomical units. The distance to the next star is 268,000 astronomical units. Our Sun's bubble of influence occupies less than 0.1% of the distance to the nearest neighbouring star. Everything else, the remaining 99.9% of the space between here and Proxima Centauri, belongs to the interstellar medium. Our Sun's protective sphere is a tiny dimple pressed into an ocean that stretches to the horizon in every direction. But even the heliosphere is not the outermost feature associated with the solar system. Far beyond the planets, far beyond the heliopause where the Voyagers crossed into interstellar space, a vast and ghostly structure is believed to surround our Sun. The Oort cloud is a theoretical shell of icy bodies, thought to extend from roughly 2,000 astronomical units out to perhaps 50,000 or even 100,000 astronomical units from the Sun. At its outer edge, that is nearly 1.5 light-years from the Sun, approaching halfway to Proxima Centauri. These frozen objects, remnants from the solar system's formation 4.5 billion years ago, orbit so far from the Sun that its gravitational pull on them is barely stronger than the gravitational influence of passing stars and the overall tidal field of the Milky Way itself. A gentle nudge from a distant stellar flyby can send one of these icy wanderers tumbling inward on a journey that takes millions of years to complete. eventually arriving near the Sun as a long-period comet visible from Earth for a few brief weeks before vanishing back into the darkness. The Oort cloud has never been directly observed. No telescope has imaged it. No spacecraft has come remotely close to reaching it. Voyager 1, after nearly 50 years of flight, has travelled barely 1/100th of the distance to the Oort cloud's inner edge. The cloud's existence is inferred from the orbits of long-period comets that occasionally plunge inward toward the Sun from random directions, arriving from above, below, and every angle of the ecliptic plane, suggesting a roughly spherical reservoir of icy bodies at extreme distances. If it exists as theorized, the Oort cloud defines the absolute outermost gravitational boundary of the solar system, a sphere roughly 2 to 3 light-years in diameter. That is a substantial distance. But even this enormous structure, even the most generous possible definition of the solar system's total extent, remains utterly dwarfed by the larger environment surrounding it. The feature that our solar system is embedded inside stretches over 1,000 light-years across. The entire solar system, from the Sun out to the farthest hypothetical Oort cloud object, would fit inside that larger structure more than 300 times over. You could line up hundreds of solar systems end to end, each one stretching from its central star to the outermost fringe of its cometary halo, and still not span the diameter of the environment we are drifting through right now. This is not a subtle difference in scale. This is not a matter of the solar system being slightly smaller than the next level of cosmic organization. This is a difference so vast that it renders the entire solar system, everything we know, everything we have ever explored, everything visible through every telescope humanity has ever pointed at the sky, microscopic by comparison. If you shrank the larger surrounding structure down to the size of a football field, the solar system, including the full extent of the Oort cloud, would be no larger than a grapefruit sitting on the 50-yard line. And the planetary system, the part with the actual worlds, would be invisible to the naked eye entirely. You would need a microscope to find Earth. The interstellar medium does not merely surround the heliosphere at a respectful distance, it actively interacts with it. The solar system is currently moving through the local interstellar material at a speed of approximately 26 kilometers per second, heading in a direction roughly toward the constellation Scorpius. This motion creates an interstellar wind, a steady flow of gas and dust that streams past and through the solar system continuously. Neutral atoms from the interstellar medium, primarily hydrogen and helium, carry no electric charge and therefore are not deflected by the Sun's magnetic field or repelled by the solar wind. They pass straight through the heliopause as though it did not exist and penetrate deep into the solar system. Some reach as close as Earth's orbit before being ionized by solar ultraviolet radiation and swept up by the solar wind. Others pass even closer to the Sun before being destroyed. Scientists have directly measured this interstellar wind using instruments aboard multiple spacecraft. Multiple spacecraft over the past 3 decades have detected interstellar helium and hydrogen atoms flowing into the solar system and measured their speed, direction, and temperature. Missions like NASA's Interstellar Boundary Explorer and the recently launched Interstellar Mapping and Acceleration Probe are specifically designed to map how the heliosphere interacts with the galactic material pressing against it. From all sides. These missions are not studying distant cosmic phenomena. They are studying the immediate environment surrounding our home, an environment most people do not even know exists. The interaction between the heliosphere and the interstellar medium is not gentle or static. The heliosphere flexes and deforms in response to changing conditions on both sides of the boundary. When the Sun is more active, during solar maximum in its roughly 11-year activity cycle, the solar wind strengthens and the heliosphere inflates slightly outward. When the Sun is quieter, the heliosphere contracts inward. The interstellar medium pushes back constantly, compressing the heliosphere on the side facing our direction of travel through the galaxy and stretching it into a long tail on the opposite side. The shape that results is not the elegant sphere you might imagine. Earlier models predicted a comet-like structure with a pointed nose and a long streaming tail. More recent analysis, incorporating data from the Cassini mission and IBEX, suggests the heliosphere may be more rounded and blunt-nosed than previously thought, shaped significantly by the pressure of the interstellar magnetic field wrapping around it and constraining its expansion. This means the boundary of our sun's influence is not fixed in space. It is not a wall. It is not a permanent border. It is a dynamic, breathing membrane that responds continuously to forces originating far beyond the solar system. During a powerful solar storm, the heliosphere can push outward by millions of miles. During prolonged solar minimum, it can contract inward, potentially exposing the outer solar system to denser interstellar conditions. The interstellar medium is not simply out there somewhere, far away and irrelevant to daily life. It is in direct physical contact with the outermost reaches of our sun's domain. Pieces of it flow through the solar system every second of every day. Interstellar dust grains have been captured and analysed by instruments aboard interplanetary spacecraft. Interstellar helium atoms have been counted and catalogued. The galaxy is not on the other side of a distant border. It is here, inside our home, streaming through the spaces between our planets. And it has been shaping the conditions at the heliosphere's boundary for as long as the sun has been burning. But here is what makes all of this merely the introduction to a much larger and far stranger story. The interstellar medium immediately surrounding our solar system is not typical. It is not average. It is not what you would find in most other parts of the galaxy. Our sun, our planets, and everything we have ever known exist inside a specific region of the interstellar medium that is radically different from normal galactic conditions. The gas around us is far hotter than it should be. The density is far lower than the galactic average, not just slightly lower, but dramatically lower, roughly 1/10 the normal concentration of hydrogen atoms. The chemistry, the temperature, the pressure, the entire physical character of this particular region is extraordinary. It was shaped by cataclysmic events that occurred millions of years before humans evolved, events so violent they reshaped hundreds of cubic light-years of galactic real estate. The solar system is not floating in generic interstellar space. It is floating inside a particular structure within interstellar space. A vast cavity blown open by the deaths of massive stars, heated to temperatures exceeding 1 million degrees, emptied of nearly all the cold dense gas that would normally fill this volume of the galaxy. This structure has a name. It has been mapped in 3 dimensions using data from the Gaia Space Observatory and multiple X-ray telescopes. Its boundaries have been traced. Its origin has been modelled by astrophysicists and confirmed by radioactive isotopes found in Earth's own deep-sea geology. And its scale makes the solar system look like a single bacterium clinging to the wall of an empty warehouse. Most people have never heard of it. Most people go their entire lives imagining the solar system surrounded by simple, featureless darkness. They never learn that the darkness itself has structure, that the apparent emptiness has a shape, a temperature, a violent origin story, and a name, that our sun and its planets are not drifting through nothing, but drifting through the interior of something specific, something enormous, something that was created by destruction on a scale that dwarfs anything in human experience. What is this hidden environment? How was it made? How large is it really? And how do scientists know it exists when it is almost entirely invisible to everything except specialized instruments most people have never heard of? The answers begin with a mysterious glow that nobody could explain. A faint X-ray signal detected in the 1970s, coming from every direction in the sky simultaneously, too uniform to originate from distant galaxies, too bright to come from nothing at all. A signal that could only mean one thing. The space immediately surrounding our solar system was filled with superheated plasma, gas hotter than the surface of most stars in the galaxy. And the source of that heat was not our sun. It was something far more violent, something ancient, something dead. And it left behind a cavity large enough to swallow everything we have ever known. In 1972, a team of physicists launched a small experiment aboard a sounding rocket from White Sands, New Mexico. The instrument was designed to detect soft X-rays, extremely low-energy X-ray photons that cannot penetrate Earth's atmosphere and must be observed from above it. The flight lasted only a few minutes. The rocket arced into the upper atmosphere, the instrument gathered data, and the payload parachuted back to the desert floor. The scientists expected to detect X-rays from known cosmic sources, distant galaxies, hot gas in galaxy clusters, the faint remnants of supernova explosions elsewhere in the Milky Way. They found all of those signals, but they also found something else. Something that should not have been there, coming from every direction in the sky uniformly with no obvious source, was a faint but unmistakable glow of soft X-ray radiation. It was not concentrated in any particular direction. It did not come from any known object. It arrived from above, below, left, right, toward the galactic center and away from it, from the plane of the Milky Way, and from the empty regions far above and below the disk. The glow was everywhere, and it was far too bright to be explained by the combined emission of distant, unresolved sources. Something close to the solar system, something local, something surrounding us on all sides, was producing X-rays. This was baffling. X-ray emission at these wavelengths requires gas heated to temperatures of roughly 1 million Kelvin. That is hotter than the surface of most stars. The Sun's visible surface sits at about 5,800 Kelvin. The corona, the Sun's outer atmosphere, reaches 1 to 2 million Kelvin, but its X-ray emission is concentrated in a small area of sky around the Sun. The diffuse glow detected by the sounding rocket came from everywhere. It was not the Sun. It was not a single distant object. It was the space itself, the interstellar medium in the immediate vicinity of the solar system, glowing faintly with the thermal radiation of extraordinarily hot plasma. The discovery created a puzzle that would take nearly 50 years to fully resolve. If the space around the Sun is filled with million-degree plasma, something must have heated it. Ordinary interstellar gas does not reach those temperatures on its own. You need an event of extraordinary violence to heat gas to 1 million Kelvin and keep it that hot for any significant period of time. The energy required is immense. The only astrophysical process capable of delivering that much energy to a region of interstellar space is a supernova explosion. The catastrophic death of a massive star that releases more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. But a single supernova could not explain the observations. A single explosion would create a hot region in one direction, a bright patch of X-ray emission concentrated around the site of the blast. The observed glow was uniform in every direction. Whatever created it had to surround the solar system completely, wrapping around us in all 3 dimensions. That required not one explosion, but many. Multiple supernovae detonating over millions of years in roughly the same region of the galaxy, each one adding its energy to the expanding shell of hot gas, each one pushing the surrounding interstellar medium farther outward, each one contributing to the creation of an enormous cavity, centered approximately where the Sun happens to be located today. Scientists gave this cavity a name. They called it the local bubble. The local bubble is a real, physically measurable structure in the interstellar medium of the Milky Way. It is a vast cavity of extremely low density, extremely high temperature plasma embedded within the denser, cooler gas that fills most of the galaxy's disk. Its existence has been confirmed by multiple independent lines of evidence accumulated over 5 decades of observation. It is not a hypothesis. It is not a theoretical prediction awaiting confirmation. It is a mapped, measured, 3-dimensionally modelled feature of our galactic neighbourhood. The basic physical properties of the local bubble are striking in their extremity. The average density of neutral hydrogen inside the bubble is approximately 0.05 of an atom per cubic centimetre. The average density of neutral hydrogen in the normal interstellar medium of the Milky Way is roughly 0.5 an atom per cubic centimetre. The local bubble is therefore about 10 times emptier than the galactic average. In some directions, the density drops even lower. Certain regions within the bubble contain gas at densities approaching 1,000th of an atom per cubic centimetre. hundreds of times emptier than typical interstellar space. The material that should be here, the cold neutral gas that fills most of the galaxy between stars, has been swept away, cleared out, blasted to the edges by forces that operated millions of years before any human being drew breath. The temperature compensates for the missing density in a dramatic way. The plasma filling the local bubble has been heated to temperatures between roughly 700,000 and 2 million Kelvin, depending on direction and location within the cavity. Recent measurements from the eROSITA X-ray telescope, published in the journal Astronomy and Astrophysics, found that the bubble's temperature is not uniform. There is a clear gradient, with the southern galactic hemisphere registering a mean plasma temperature of approximately 1.4 million Kelvin, and the northern hemisphere measuring roughly 1.2 million Kelvin. This temperature asymmetry suggests the bubble was not inflated by a single symmetric blast, but shaped by multiple explosions occurring at different times and locations, each one heating different portions of the cavity to different degrees. Despite these extraordinary temperatures, you would feel nothing if you could stand inside the bubble's plasma unprotected. Temperature in physics describes the average kinetic energy of individual particles. At 1 million Kelvin, each proton and electron in the plasma moves at tremendous speed. But there are so few of them per cubic centimeter that the total thermal energy contained in any human-sized volume is negligible. You would radiate your own body heat into the near vacuum far faster than the sparse plasma could warm you. The local bubble is a place of paradox, a region defined simultaneously by unimaginable heat and unimaginable emptiness, where temperatures exceeding those at the surface of every star in the galaxy coexist with densities lower than anything humans can manufacture in a laboratory. The size of the local bubble varies depending on direction, because the cavity is not spherical. Early models assumed a roughly round shape, but decades of increasingly precise measurements have revealed a far more complex geometry. The bubble appears to be narrower in the plane of the Milky Way's disk, where the surrounding interstellar medium is densest and most resistant to being pushed aside. In these directions, the cavity extends roughly 300 to 400 light-years from the Sun before encountering the denser walls of gas and dust that define its boundary. Above and below the galactic plane, where the surrounding medium is thinner and offers less resistance, the bubble extends much farther. In some directions perpendicular to the disk, the cavity may stretch 600, 800, or even 1,000 light-years before reaching its boundary. The overall shape has been described as resembling an hourglass or an elongated egg, narrow at the waist where the galactic disk compresses it, and widening into lobes above and below the plane. Some researchers have suggested the bubble may not be closed at all in the vertical directions. It might be open-ended, venting hot gas upward and downward into the galactic halo like a chimney, forming what some scientists call a local tube rather than a local bubble. This would connect the cavity directly to the vast regions of thin, hot gas that exist above and below the Milky Way's disk, making it part of a larger circulatory system that moves energy and material between the galaxy's dense midplane and its diffuse outer atmosphere. But the most remarkable fact about the local bubble is not its temperature, its density, its shape, or its size considered individually. It is what created it, and what that creation is still doing right now. The origin of the local bubble has been a subject of scientific investigation since its discovery. The leading explanation, now strongly supported by observational evidence, is that the cavity was carved out by a series of supernova explosions beginning approximately 14 million years ago. These were not random explosions scattered across the galaxy. They originated from a specific concentration of massive stars belonging to stellar associations in what is now the Scorpius-Centaurus region of the sky, the nearest large grouping of young, massive stars to the Sun. Massive stars, those born with more than roughly 8 times the mass of our Sun, live fast and die violently. A star 20 times the Sun's mass might burn through its nuclear fuel in just 10 million years, compared to the Sun's 10 billion-year lifespan. When such a star exhausts its fuel, its core collapses in a fraction of a second, triggering an explosion that ejects the star's outer layers at speeds exceeding 10,000 kilometers per second. The energy released in a single supernova equals approximately 10 to the 46 joules, a number so large it defies useful comparison. It is more energy than the Sun will radiate in its entire main sequence lifetime, compressed into a blast lasting seconds. When a supernova detonates inside the interstellar medium, the shock wave races outward in all directions at thousands of kilometers per second, slamming into the surrounding gas with a force that is almost impossible to overstate. The collision heats the gas to millions of degrees and accelerates it outward, sweeping it up like a snowplow clearing a road after a blizzard. Behind the expanding shock wave, a cavity forms, a region emptied of its original cold gas and filled instead with the superheated plasma left in the explosion's wake. Over thousands of years, the cavity grows as the shock wave pushes farther and farther into the surrounding medium, decelerating gradually as it encounters resistance but still carrying enough momentum to reshape the interstellar landscape across dozens of light years. Eventually, the shock wave slows to the point where it can no longer overcome the pressure of the surrounding gas. The cavity stops expanding, and the hot interior begins the long, slow process of cooling back toward equilibrium. A single supernova can excavate a cavity tens of light years across and keep it hot for hundreds of thousands of years. Impressive, but nowhere near the scale of the local bubble. The key insight is that the Scorpius-Centaurus association did not produce just one supernova. Stellar associations contain dozens or hundreds of massive stars born from the same giant molecular cloud at roughly the same time. These stars age and die in sequence, the most massive exploding first, followed by progressively less massive siblings over millions of years. Current models estimate that between 14 and 20 supernovae from the lower Centaurus Crux and upper Centaurus Lupus subgroups of the Scorpius-Centaurus association detonated over a span of several million years, each one injecting its energy into the expanding cavity left by its predecessors. The cumulative effect was devastating. Each new explosion reheated the gas inside the growing cavity, preventing it from cooling and collapsing. Each new shockwave pushed the cavity walls farther outward, sweeping up more interstellar material and piling it onto the dense shell surrounding the void. The supernovae did not need to happen simultaneously. They happened in sequence, a chain of stellar deaths spread across millions of years, each one building on the work of the last. The result was not a small hot patch in the interstellar medium. The result was a monstrous cavity stretching hundreds of light years in every direction, emptied of its original material, filled with million-degree plasma, and still expanding today. This picture received its most dramatic confirmation in January 2022, when a team led by Catherine Zucker at the Center for Astrophysics at Harvard and the Smithsonian published a landmark paper in the journal Nature. Using three-dimensional spatial data from the European Space Agency's Gaia spacecraft combined with newly constructed maps of interstellar dust, Zucker and her colleagues built the most detailed three-dimensional model of the local bubble ever produced. Their analysis revealed two extraordinary findings. First, they confirmed that the bubble was created by a burst of supernovae beginning approximately 14 million years ago near its current center. By tracing the motions of young stars near the bubble backward in time, the researchers showed that the explosion site was consistent with the known location of the Scorpius-Centaurus stellar associations. The timing, the location, and the energy requirements all matched. The sequence of events that created the local bubble was no longer a plausible hypothesis. It was a reconstructed history, supported by the measured trajectories of real stars observed by a real spacecraft. Second, and even more remarkably, Zucker's team found that nearly all of the star-forming molecular clouds within roughly 600 light-years of the Sun sit on the surface of the local bubble, not near the bubble, not inside the bubble. On its surface, the Taurus molecular cloud, the Ophiuchus cloud complex, the Lupus clouds, the Corona Australis cloud, the Chamaeleon complex, the Musker Cloud. Every one of these well-known stellar nurseries, regions where new stars are actively being born today, lines the outer shell of the expanding cavity, and the young stars emerging from these clouds are moving outward, perpendicular to the bubble's surface, carried along by its continued expansion. This means the local bubble is not a dead relic. It is not an ancient scar left behind by long-vanished explosions. It is an active engine of star formation, still expanding at roughly 6.5 kilometers per second, still sweeping up interstellar gas and compressing it against its outer wall, still triggering the gravitational collapse of dense clouds that produces entirely new generations of stars. The supernovae that created the bubble destroyed whatever was here before, but in doing so, they set in motion a process that is now building something new. The deaths of massive stars 14 million years ago directly caused the births of stars that are forming at this very moment. Destruction and creation operating as two phases of the same event, separated by millions of years but connected by the expanding shell of a single, enormous cavity. The Sun's presence near the center of the local bubble is, as the researchers carefully noted, a coincidence. The Sun did not form here. The solar system is 4.5 billion years old, 300 times older than the bubble itself. When the first supernovae began detonating 14 million years ago, the Sun was elsewhere in its orbit around the galactic center. Over the intervening millions of years, the Sun's path through the galaxy carried it into the region that had been cleared by the explosions. Current estimates suggest the solar system entered the local bubble between roughly 5 and 10 million years ago, drifting in from the outside through the cavity wall and into the hot, sparse interior where it now resides. This means we are visitors. We did not grow up inside the bubble. We wandered into it, and the conditions we experience as normal, the local density of the interstellar medium, the temperature of the gas surrounding the heliosphere, the intensity of the soft X-ray background glowing from every direction, none of this is typical of the galaxy as a whole. It is typical of the inside of a supernova-carved cavity that happens to be our current address. A few million years ago, the solar system was embedded in denser, cooler interstellar gas. A few million years from now, as the Sun continues its orbit, it may leave the bubble entirely and enter a completely different interstellar environment. But the local bubble's story did not end with the Zucker paper. New observations have continued to reveal that the cavity is even more complex and connected than earlier models suggested. In 2024, a team led by Michael Jung at the Max Planck Institute for Extraterrestrial Physics published a groundbreaking analysis using data from the eROSITA X-ray telescope aboard the Spectrum Roentgen Gamma Observatory. The eROSITA instrument conducted the most detailed soft X-ray survey of the sky ever performed, scanning the entire celestial sphere from its vantage point at the Sun-Earth Lagrange point L2, far above the interfering glow of Earth's atmosphere. Jung's team divided the Western Galactic Hemisphere into approximately 2,000 spatial bins and extracted the X-ray spectrum from each one, building a high-resolution map of the hot plasma surrounding the solar system. They combined this data with historical observations from the Rosat satellite, eROSITA's predecessor, and integrated neutral hydrogen and dust measurements from the High 4Pi and Planck surveys. The result was the most detailed three-dimensional model of the local bubble's hot interior ever constructed. The findings went beyond confirming what was already known. The team discovered something new. Extending outward from the local bubble toward the constellation Centaurus, they found evidence for an elongated channel of hot, low-density plasma cutting through the surrounding cooler interstellar medium. This structure, which they described as an interstellar tunnel, appears to connect the local bubble to a neighbouring superbubble, a larger cavity formed by a different cluster of ancient stellar explosions. A second possible channel was detected extending toward the constellation Canis Major, potentially linking the local bubble to the Gum Nebula region approximately 1,500 light-years away. The existence of these tunnels was not entirely unexpected. As far back as the 1970s, theoretical astrophysicists had proposed that the interstellar medium of the Milky Way might be threaded by a network of interconnected cavities, each one blown open by supernovae in different stellar associations, with tunnels of hot plasma connecting them through the cooler gas in between. The idea was compelling but extremely difficult to test. The structures involved are faint, diffuse, and spread across enormous areas of sky. Previous X-ray telescopes lacked the sensitivity and resolution to map them clearly. The eROSITA data changed that. For the first time, instruments existed that could resolve the subtle temperature and density variations within the local bubble in enough detail to detect these connecting corridors. The implications are significant. If the local bubble is connected to neighboring cavities through interstellar tunnels, then our solar neighborhood is not an isolated pocket of hot gas surrounded by cold walls. It is part of a larger network, a porous web of interconnected hot chambers stretching across hundreds or thousands of light years of the galactic disk. Hot plasma, cosmic rays, and magnetic fields could flow through these tunnels, linking regions that might otherwise seem completely separate. The galaxy's interstellar medium is not a simple two-phase system of hot bubbles and cold clouds sitting side by side. It is an interconnected structure, a three-dimensional maze of cavities and corridors constantly being reshaped by the explosions of massive stars. The eROSITA team also confirmed the temperature asymmetry within the local bubble, with the southern galactic hemisphere measuring significantly hotter than the north. This asymmetry likely reflects the specific history of supernova explosions that shaped the cavity. Numerical simulations suggest that explosions occurring within the last few million years, more recent than the original chain that created the bubble, may have preferentially heated the southern hemisphere. The bubble is not a static relic. It is a structure with ongoing dynamics, still being modified by energy inputs, and still evolving in response to forces that operate on timescales of millions of years. Understanding the local bubble also required solving a decades-long scientific controversy about the origin of the soft X-ray background that first revealed its existence. Throughout the 1980s and 90s, the standard explanation was straightforward. The X-rays came from hot plasma inside the local bubble, glowing faintly as the million-degree gas radiated its thermal energy. But in 1996, scientists discovered a competing process that could also produce soft X-rays near Earth. When highly charged ions in the solar wind collide with neutral atoms in Earth's outer atmosphere or in the interstellar gas flowing through the solar system, they can emit X-ray photons through a mechanism called solar wind charge exchange. This process occurs within the solar system itself, not in the surrounding interstellar medium, and it produces X-rays at energies very similar to those expected from the local bubble's plasma. The discovery of charge exchange threw the entire field into confusion. If a significant portion of the observed soft X-ray background was actually being produced locally within the heliosphere, then the amount of hot plasma required in the surrounding interstellar medium might be much less than previously assumed. Some researchers even questioned whether the local bubble needed to contain million-degree plasma at all. Perhaps the entire soft X-ray background could be explained by charge exchange, and the bubble was simply a low-density cavity without any particularly hot gas filling it. Resolving this debate required carefully separating the two signals. Charge exchange emission varies with the solar wind's intensity and with Earth's position relative to the incoming interstellar gas flow. It should therefore change over time, fluctuating with solar activity and Earth's orbital position. The bubble's thermal emission, by contrast, should remain constant because the surrounding plasma does not change on human timescales. By comparing observations taken at different times and from different vantage points, scientists gradually disentangled the two contributions. The consensus that emerged, strengthened by data from multiple missions, including the DXL sounding rocket experiment and the eROSITA survey, is that both processes contribute to the observed soft X-ray background. Charge exchange accounts for a significant fraction of the signal in certain energy bands and at certain times, but it cannot account for all of it. A substantial component of the diffuse X-ray glow genuinely originates from hot plasma in the local bubble. The cavity is real. The million-degree gas filling it is real. and its influence on our solar system's environment is real and measurable. The confirmation of the local bubble as a physical, three-dimensionally mapped, supernova-carved cavity surrounding our solar system is one of the most remarkable discoveries in modern astrophysics. Not because the bubble is unique, as we will see the galaxy is filled with similar structures, but because of what it reveals about the hidden environment that has surrounded humanity for our entire existence as a species without our ever being aware of it. Consider the situation plainly. Every human being who has ever lived was born inside this cavity. Every civilization in human history, from the first settlements in Mesopotamia to the launch of the James Webb Space Telescope, has occurred while the solar system drifted through the interior of a supernova-blasted void over 1,000 light-years across. The night sky that inspired ancient mythology, the stars that guided oceanic navigation, the cosmos that modern telescopes have mapped in exquisite detail, all of it was observed from within this invisible structure. And yet for the vast majority of human history, nobody knew it was there. Nobody suspected that the apparently empty darkness between the stars had a specific character, a specific origin, a specific name. The local bubble is not something we look at through a telescope. It is something we look through. It is the medium through which every astronomical observation ever made has been conducted. It is the environment that determines the local density of the interstellar gas pressing against our heliosphere. It is the reason the soft X-ray sky looks the way it does. And it is a direct product of the most violent events that have occurred in our galactic neighborhood in the last 20 million years. But the bubble is not empty. The cavity that supernovae blasted open is not a perfect void. Floating within it, drifting through the million-degree plasma, like wisps of fog in a heated room, are small clouds of cooler, denser gas. These clouds are remnants, survivors, fragments of the interstellar material that was not completely destroyed or swept away when the explosions carved out the cavity. And the solar system is not merely inside the local bubble in general terms. Right now, at this very moment, it is passing through one of these surviving clouds, a small warm cloudlet of partially ionized gas that is itself embedded within the larger cavity. This cloud has a name. It is called the local interstellar cloud, and its interaction with our solar system, its influence on the heliosphere, and the evidence it has left in Earth's own geology form the next layer of this story. The solar system is inside a bubble, yes, but inside that bubble it is also inside a cloud, and inside that cloud it is wrapped in yet another layer of protection, the heliosphere, which has been shaped and compressed and occasionally overwhelmed by the conditions it encounters as the sun moves through these nested structures at 26 kilometers per second. The layers go deeper than anyone imagined, and the evidence goes all the way down to the bottom of the ocean. The local bubble is not hollow. That is the first thing you need to understand about the interior of this enormous cavity. When supernovae blasted out the cold, dense gas that once filled this region of the galaxy, they did not remove every last trace of material. They could not. The explosions were powerful enough to sweep most of the interstellar medium outward and pile it onto the bubble's expanding shell, but pockets of gas survived. Small clumps of material too dense to be fully dispersed, or fragments created later when different expanding structures collided and compressed gas between them, persisted inside the cavity. These surviving remnants drift through the million-degree plasma of the bubble's interior like islands of relative coolness in an ocean of superheated emptiness. They are small by galactic standards, typically just a few light-years across, and they are warm rather than hot, thousands of degrees rather than millions. But they are real, and the solar system is passing through one of them right now. The cloud is called the local interstellar cloud. Sometimes astronomers refer to it simply as the LIC. It is a wisp of partially ionized gas roughly 30 light-years across, drifting through the interior of the local bubble at a velocity that differs slightly from the sun's own motion through space. The relative motion between the sun and the cloud is what creates the interstellar wind that streams through our planetary neighborhood. The Sun entered the local interstellar cloud at some point within the past few tens of thousands of years, though the exact moment of entry is difficult to pinpoint because the cloud's boundaries are not sharp walls but gradual transitions in density and temperature. Depending on the cloud's precise dimensions and the exact trajectory of the solar system through it, we may exit the cloud within the next 10,000 to 20,000 years. The Sun currently sits only about 4 light-years from the cloud's nearest edge, a distance that could be crossed in a cosmically brief interval. On cosmic timescales, our passage through this cloud is a brief encounter, a momentary immersion that will end as the Sun's orbit carries it onward, through the bubble's interior toward whatever environment lies ahead. The physical properties of the local interstellar cloud are exceptionally well measured, far better than those of almost any other interstellar structure, precisely because we are inside it. Its gas flows directly through the solar system, and instruments on spacecraft have sampled it with a directness that astronomers studying distant nebulae can only envy. The cloud's temperature is approximately 6,000 to 7,000 Kelvin, warm enough to partially strip electrons from hydrogen and helium atoms, but cool enough that a significant fraction of the gas remains neutral. Its density is roughly 0.3 of an atom per cubic centimetre, which makes it about 6 times denser than the surrounding bubble plasma, but still far thinner than the average interstellar medium of the galaxy. The cloud is composed primarily of hydrogen and helium, with traces of heavier elements including oxygen, nitrogen, carbon, and iron. About 30% of the hydrogen in the cloud is ionized, meaning it has lost its electron and exists as free protons. The remaining 70% is neutral atomic hydrogen, and it is this neutral component that flows freely through the heliosphere because neutral atoms are invisible to magnetic fields. The local interstellar cloud is not alone inside the bubble. Several other small cloudlets have been identified in its vicinity, each one a discrete concentration of warm gas floating through the hot cavity, like individual clumps of mist drifting through the interior of a vast heated greenhouse. The most prominent neighbour is called the G-cloud, a similar wisp of partially ionized material lying just a few light-years from the Sun in the direction of the galactic centre. The G-cloud has slightly different physical properties than the local interstellar cloud, with a somewhat different temperature and velocity, suggesting it is a separate structure rather than a continuous extension of the same cloud. The boundary between the two clouds may lie very close to the solar system's current position, and some researchers have suggested that the Sun may be transitioning from one cloud to the other at this very moment, crossing a thin interface between two distinct parcels of interstellar gas. Other named structures in the vicinity include the Blue Cloud, the Aquila Rift extension, and the Mike Cloud. Additional unnamed cloudlets have been detected through ultraviolet absorption measurements toward nearby stars, their presence revealed by the characteristic fingerprints they leave in starlight passing through them. Together, these cloudlets form what astronomers sometimes call the local fluff, a loose complex of warm gas fragments clustered in the part of the bubble where the Sun currently resides. The local fluff is not a single coherent structure but a collection of independent clouds, each a few light-years across, each moving on its own trajectory through the bubble's interior, each one a surviving remnant of the interstellar material that once filled this now evacuated region of the galaxy. The origin of these cloudlets is connected to the bubble's own history. The local interstellar cloud and the G-cloud appear to have formed in a region where the local bubble and a neighbouring structure called the Loop I bubble meet. The Loop I bubble is another supernova-carved cavity, created by explosions in the Scorpius-Centaurus stellar association, the same group of massive stars responsible for many of the blasts that excavated the local bubble itself. Where these two expanding cavities pressed against each other, the gas between them was compressed, heated, and partially ionized. The local interstellar cloud is thought to be a fragment of this compressed interaction zone, a piece of the boundary between two colliding superbubbles that broke off and now drifts through the local bubble's interior. This means the little cloud surrounding our solar system was itself created by the same chain of stellar violence that carved out the larger cavity. The supernovae that blasted open the local bubble also created the conditions that formed the cloud we are now passing through. Everything in our immediate interstellar environment, the bubble, the cloud, the hot plasma, the compressed shell where new stars are being born, traces back to the same sequence of massive stellar deaths that began 14 million years ago in a cluster of young stars that no longer exists. The flow of interstellar material through the solar system is not a theoretical inference or a prediction from computer models waiting to be confirmed. It is a directly observed phenomenon, measured repeatedly with increasing precision by multiple spacecraft over the course of several decades. Because the solar system is moving through the local interstellar cloud at approximately 26 kilometers per second, interstellar gas streams past and through our neighborhood continuously. This creates what astronomers call the local interstellar wind, a steady directional flow of atoms arriving from a point in the sky near the constellation Scorpius, roughly aligned with the direction the Sun is traveling through space. The wind consists primarily of neutral hydrogen and neutral helium atoms from the cloud. These particles carry no electric charge, so they are unaffected by the Sun's magnetic field and pass through the heliosphere's magnetic boundary as though it were not there. Neutral helium atoms penetrate all the way to within roughly half an astronomical unit of the Sun, before solar gravity focuses them into a concentrated downstream cone on the opposite side from the incoming flow. This focusing effect was first detected by the Ulysses spacecraft in the early 1990s, confirming that interstellar helium was flowing through the inner solar system in measurable quantities. The density of interstellar helium detected near Earth varies slightly over the course of the year, as our planet moves through the focus cone and then away from it, creating a seasonal signal in the interstellar wind. Neutral hydrogen atoms behave differently because they are more easily ionized by solar ultraviolet radiation. Hydrogen atoms from the interstellar wind lose their electrons at greater distances from the Sun, typically beyond a few astronomical units. Once ionized, the former interstellar atoms become charged particles that are immediately picked up by the solar wind's magnetic field. These pickup ions, as they are called, are accelerated and swept outward by the solar wind, carrying with them information about the density and composition of the interstellar medium that they originally came from. Instruments aboard the Advanced Composition Explorer spacecraft and other missions have detected these pickup ions and used them to measure the properties of the interstellar gas entering the solar system. Even interstellar dust penetrates the heliosphere. Grains of silicate and carbon material from the local interstellar cloud, each one typically less than a micrometer in diameter, stream into the solar system along with the gas. These grains are electrically charged by ultraviolet radiation and interact with the solar wind's magnetic field, which filters and deflects them in complex ways that depend on the grain size, the solar cycle phase, and the magnetic field's polarity. The Ulysses, Galileo, and Cassini spacecraft all detected interstellar dust grains passing through the solar system. The Stardust mission, launched in 1999, even attempted to capture interstellar particles using an aerogel collector. An analysis of the returned samples identified a small number of grains whose composition was consistent with an interstellar origin. The presence of interstellar material flowing continuously through our planetary neighborhood means the solar system is not sealed off from its galactic environment. It never has been. The heliosphere deflects charged particles and modifies the flow of dust, but it cannot stop neutral atoms from entering freely. Roughly 98% of the neutral gas within the heliosphere at any given time is interstellar in origin, not solar. The space between the planets, the region we think of as belonging exclusively to our Sun, is overwhelmingly filled with material from outside. The galaxy reaches in. It has always reached in. We simply lacked the instruments to detect it until the last few decades of space exploration. NASA's Interstellar Boundary Explorer, IBEX, launched in 2008, has been mapping the interaction between the heliosphere and the interstellar medium for over 17 years. IBEX detects energetic neutral atoms created when solar wind ions collide with interstellar neutral atoms at the heliosphere's boundary. These energetic neutrals travel back toward Earth in straight lines, allowing IBEX to construct maps of the heliosphere's outer boundary as seen from the inside. The maps revealed unexpected features, including a bright ribbon of energetic neutral atom emission that appears to trace the direction of the interstellar magnetic field pressing against the heliosphere from outside. This ribbon was not predicted by any model before IBEX's launch. Its existence demonstrates that the interstellar magnetic field, a feature of the local interstellar cloud, and the broader local bubble environment, directly shapes the structure of our heliosphere in ways that scientists are still working to fully understand. The next generation mission, NASA's Interstellar Mapping and Acceleration Probe, IMAP, is designed to map the heliosphere's boundary with 10 times the resolution of IBEX. It will provide unprecedented detail about how the solar wind interacts with interstellar material and how the heliosphere responds to changing conditions in the surrounding cloud. IMAP represents humanity's most sophisticated attempt yet to characterize the environment that lies just beyond the edge of our sun's protective influence, the environment that has surrounded us invisibly for the entire history of our species. But the most astonishing evidence of the local bubble's influence on our solar system does not come from spacecraft orbiting above Earth's atmosphere. It comes from the bottom of the ocean. In the late 1990s, scientists analyzing deep-sea sediment cores from the Pacific Ocean floor discovered something unexpected. Embedded within layers of ferromanganese crust, the slow-growing mineral deposits that accumulate on the ocean floor at rates of a few millimeters per million years, they found elevated concentrations of iron-60. Iron-60 is a radioactive isotope of iron with a half-life of approximately 2.6 million years. It does not occur naturally on Earth in any significant quantity. No volcanic eruption produces it, no tectonic process creates it, no chemical reaction in Earth's oceans or atmosphere can generate it. Iron-60 is forged exclusively in the extreme conditions of stellar nucleosynthesis, primarily in the violent final moments of a massive star's life, when a supernova detonation fuses atomic nuclei together under pressures and temperatures that exist nowhere else in the universe. The only way iron-60 could have arrived in deep-sea sediments on Earth is if it fell from the sky, raining down through the atmosphere and settling to the ocean floor after being ejected from a dying star somewhere in our galactic neighborhood and carried across interstellar space to our doorstep. The discovery sent shockwaves through the astrophysics and geoscience communities simultaneously. It was one thing to know theoretically that the solar system exists within a supernova-carved cavity. It was something else entirely to hold the physical residue of those explosions in your hands, extracted from the geological record of our own planet. Radioactive debris from a supernova, found in the mud at the bottom of Earth's oceans, meant that a massive star had exploded close enough to the solar system to shower our planet with freshly synthesized atomic material. Not in the distant past, not billions of years ago when the solar system was forming from its own ancestral molecular cloud, but recently, geologically recently, within the last few million years. The iron-60 deposits could be dated by the layers of sediment above and below them, and the dates pointed to specific windows in time. 2 distinct peaks of iron-60 concentration were identified. The more recent peak corresponds to roughly 1.7 to 3.2 million years ago. The older peak dates to approximately 6.5 to 8.7 million years ago. These are not vague or approximate estimates. The ferromanganese crusts grow at known rates. The layers can be cross-referenced with other dating techniques, including beryllium-10 decay. The timing is reliable. Additional confirmation came from other sources. Iron-60 was found in Antarctic snow samples, deposited within the last few million years. It was detected in lunar soil returned by the Apollo missions, consistent with a recent influx of supernova debris across the entire inner solar system. And manganese-53, another radioactive isotope produced by supernovae with a half-life of 3.7 million years, was found in the same deep-sea sediment layers, peaking at the same dates. Multiple isotopes, multiple locations, multiple independent measurements, all pointing to the same conclusion. Nearby supernovae deposited radioactive material on Earth at specific times within the last 10 million years. The connection to the local bubble was immediately apparent. The bubble was carved by supernovae from the Scorpius-Centaurus stellar association beginning 14 million years ago, with explosions continuing over millions of years. The timing of the Iron 60 peaks falls within the later stages of this sequence. The older peak, 6.5 to 8.7 million years ago, likely corresponds to the solar system passing through the enriched outer shell of the local bubble as it entered the cavity from outside. The younger peak, 1.7 to 3.2 million years ago, is attributed to a specific supernova explosion from either the Upper Centaurus Lupus or the Tucana Horologium stellar associations, occurring while the solar system was already inside the bubble. Research published in 2025 by Caitlin Nojiri and colleagues at the University of California, Santa Cruz modeled the energy output of the supernova responsible for the younger Iron 60 peak and estimated the amount of cosmic radiation Earth would have received. Their analysis, published in the astrophysical journal Letters, concluded that the progenitor star was massive enough to produce some of the highest energy cosmic rays in the universe. The cosmic radiation that rained down on Earth from this explosion would have penetrated the atmosphere and reached the surface, exposing the planet and all life on it to elevated radiation levels that persisted for thousands of years after the blast. The implications for biology are provocative and still being explored. Elevated cosmic radiation can increase mutation rates, drive genetic change, and apply selective pressure on populations. The younger Iron 60 peak at roughly 2 to 3 million years ago coincides intriguingly with a period of significant evolutionary change in Africa, including the emergence and diversification of early Homo species. Whether the supernova radiation actually contributed to evolutionary pressures on early humans remains an open question, but the temporal coincidence is striking enough that multiple research groups are actively investigating the connection. But the most dramatic interaction between the local bubble and the solar system may have occurred even further back, and its consequences may have been far more severe than a dusting of radioactive isotopes. In 2024, a team led by Mera Wolfer at Boston University published a study in the Astrophysical Journal examining what happened when the solar system crossed through the outer wall of the local bubble approximately 7 million years ago. The wall of the bubble is not empty space. It is the dense shell of swept-up interstellar material that the expanding supernova shockwaves piled up over millions of years. This shell contains cold, dense gas and dust at concentrations far higher than either the bubble's hot interior or the normal interstellar medium. Ofer's team modelled what would happen to the heliosphere if the solar system encountered a cloud of gas with a density of roughly 300 to 900 atoms per cubic centimetre, densities consistent with what might be found in the bubble's compressed outer shell. The results were startling. Under these conditions, the interstellar gas pressure would have overwhelmed the solar wind completely. The heliosphere, normally extending 100 or more astronomical units from the Sun, would have been compressed to a radius smaller than Earth's orbit around the Sun, smaller than 1 astronomical unit. The protective bubble that shields our planet from interstellar material and galactic cosmic rays would have essentially collapsed inward, shrinking inside the orbit of the very planet it is supposed to protect. Earth would have found itself outside the heliosphere for the first time in its modern geological history. Think about what that means in practical terms. For the entire span of recorded human history, for the entire span of complex multicellular life on Earth, for most of the planet's 4.5 billion year existence, Earth has orbited safely inside the heliosphere. The solar wind has always been there, pushing outward, holding the interstellar medium at bay, creating a magnetic cocoon around the inner solar system. We take this protection for granted, because it has been a constant feature of our environment for as long as anything alive has existed to notice it. But 7 million years ago, according to OFA's models, that protection temporarily vanished. This means Earth would have been directly exposed to the raw interstellar medium for a period that could have lasted thousands or even tens of thousands of years. Neutral hydrogen and helium from the dense cloud would have flooded the inner solar system, filling the space between Earth and the Sun with gas at concentrations many times higher than the wispy interstellar wind we experience today. Galactic cosmic rays, normally deflected or attenuated by the heliosphere's magnetic field, would have had unimpeded access to Earth's atmosphere. The flux of high-energy particles striking the upper atmosphere would have increased dramatically, potentially by an order of magnitude or more. These cosmic rays ionize atmospheric molecules, trigger cascades of secondary particles, and influence the formation of cloud condensation nuclei. An increase of this magnitude could have altered cloud cover patterns, changed atmospheric chemistry, and affected the amount of solar radiation reaching the surface. Interstellar dust at concentrations far higher than anything the planet normally encounters would have streamed past Earth continuously for the duration of the planet. Exposure. This dust could have scattered and absorbed sunlight at altitudes above the normal atmospheric dust layer, potentially dimming solar illumination at the surface. The atmosphere's chemistry could have been further altered by the influx of interstellar hydrogen interacting with oxygen and nitrogen at high altitudes. The effects would have been complex, interconnected, and unlike anything in Earth's normal environmental experience. The timing of this event, approximately 7 million years ago, overlaps with the older Iron 60 peak found in deep-sea sediments, supporting the interpretation that the solar system was crossing through the bubbles-enriched outer wall during this period. It also coincides with perturbations observed in Earth's paleoclimate record recovered from deep-sea sediment cores. Changes in ocean chemistry, shifts in global temperature patterns, and alterations in biological productivity during this era are consistent with a significant external influence on Earth's environment, though attributing any specific climate event to the heliosphere's collapse remains speculative at this stage. What is not speculative is the physical mechanism. The models are based on well-understood magnetohydrodynamic physics. The density estimates for the bubble's outer shell are grounded in observational data. The heliosphere's response to increased external pressure has been studied theoretically for decades and is constrained by measurements of its current interaction with the local interstellar cloud. The conclusion that the heliosphere could have been compressed inside Earth's orbit during passage through a sufficiently dense cloud is robust. Whether it actually happened at the specific time proposed depends on the precise density profile of the bubble wall along the solar system's trajectory, which remains uncertain. The broader point, however, is clear and deeply unsettling. The heliosphere is not a permanent shield, it is a conditional one. Its size and protective capability depend entirely on the balance between the outward pressure of the solar wind and the inward pressure of whatever interstellar environment the solar system happens to be passing through. Inside the local bubble, where the surrounding medium is thin and hot and exerts relatively little pressure, the heliosphere extends comfortably beyond the planets. But this comfort is a product of our current location. Move the solar system into a denser cloud, which has happened before and will happen again, and the heliosphere shrinks. Move it into a dense enough cloud and the heliosphere can collapse entirely, leaving Earth naked and unprotected in the interstellar medium. The solar system's journey through the galaxy is not a calm cruise through empty space. It is a passage through a constantly changing landscape of gas, dust, plasma, and radiation, a landscape sculpted by the explosions of dead stars into cavities, walls, clouds, and tunnels. The local bubble is one cavity. The local interstellar cloud is one cloud within that cavity. The heliosphere is one small protective membrane wrapped around one small star, and its ability to protect the planets it contains depends entirely on what it encounters as it moves. We have been inside the local bubble for only a few million years. Before that, The solar system traveled through different interstellar environments with different densities, different temperatures, different radiation fields. Millions of years from now, the Sun's orbit will carry it out of the bubble and into whatever lies beyond. The interstellar conditions surrounding our solar system are not fixed. They are not permanent. They have changed in the past, they will change in the future, and those changes have left physical evidence in the rocks beneath our feet and the sediments beneath our oceans. Iron 60 atoms forged in the heart of an exploding star, hurled outward at thousands of kilometers per second, traveling across light years of interstellar space, falling through Earth's atmosphere as invisible radioactive rain, sinking to the ocean floor, and lying there undisturbed for millions of years until a scientist on a research vessel pulled up a core sample and found them. That is not a metaphor for the connection between our solar system and its larger environment. That is the connection itself, written in radioactive ink on the pages of Earth's geological record, waiting to be read by anyone with the instruments to detect it. And this is still only the view from inside. Looking at the structures immediately surrounding the solar system, the local interstellar cloud is 30 light-years across. The local bubble is over 1,000 light-years across. But neither of these structures exists in isolation. The bubble is one cavity in a galaxy riddled with cavities. The tunnels discovered by eROSITA connect it to neighbouring structures that are themselves connected to others. The interstellar medium of the Milky Way is not a uniform fog. It is a vast, interconnected, three-dimensional architecture of bubbles, shells, tunnels, and clouds, sculpted by millions of years of stellar violence into a structure so complex that astronomers are only beginning to map its full extent. What happens when you pull back from the local bubble and look at the larger galactic environment? What does the neighbourhood around our neighbourhood actually look like? And what does the full picture reveal about how impossibly small the solar system truly is compared to the hidden world it has been travelling through all along? Pull back. Leave the local interstellar cloud behind. Leave the heliosphere behind. Rise above the plane of the solar system and keep going, accelerating outward until the sun becomes a point of light indistinguishable from any other star. Keep climbing. Pass through the warm interior of the local bubble, through the million-degree plasma that fills this enormous cavity, past the scattered cloudlets of the local fluff, drifting through the heated void. Approach the bubble's outer wall, that dense compressed shell of cold gas and dust where new stars are being born at this very moment. Pass through the wall and emerge on the other side. What do you see? You do not see open space. You do not emerge into the normal interstellar medium of the Milky Way, that average density fog of half an atom per cubic centimetre stretching uniformly to the galactic horizon. What you see instead is another bubble, and beyond that, another, and beyond that, still another. The galaxy is riddled with them. Everywhere massive stars have lived and died. Everywhere supernovae have detonated over the last several 100 million years. The interstellar medium has been blown open, heated, carved into cavities and shells and corridors of hot plasma separated by walls and filaments of cold, dense gas. The local bubble is not unusual. It is not a freak occurrence or a cosmic oddity. It is one cavity among hundreds or thousands that together define the large-scale texture of the Milky Way's interstellar medium, and the structures surrounding it tell a story about our galactic neighbourhood that makes the solar system feel even smaller than the local bubble alone ever could. Immediately adjacent to the local bubble, pressing against its boundary from the direction of the Scorpius-Centaurus Stellar Association, sits the Loop I bubble. This neighbouring cavity was created by a related but distinct sequence of supernova explosions from the same broad stellar complex that produced the local bubble. The Loop I bubble is comparable in size to our own cavity, extending several hundred light-years across and filled with its own reservoir of million-degree plasma. Its presence was first inferred from radio observations in the 1950s and 60s, when astronomers noticed a large loop of synchrotron emission arcing across the northern sky. This emission, produced by relativistic electrons, spiraling through magnetic fields at nearly the speed of light, traced the expanding shell of a superbubble, whose existence was later confirmed by X-ray observations showing hot gas filling its interior. The discovery of the eROSITA bubbles in recent years has complicated the picture somewhat, raising questions about whether all of the emission originally attributed to Loop I actually originates from a nearby superbubble, or whether some of it traces structures much closer to the galactic center. The relationship between Loop 1 and the eROSITA bubbles remains an active area of research, but the existence of a large hot cavity adjacent to the local bubble is well established. The boundary between the local bubble and the Loop I bubble is the very collision zone where, as we saw earlier, the local interstellar cloud was born. But from this wider vantage point, the interaction takes on a different character. It is not a clean wall with empty space on either side. It is a vast, ragged frontier of compressed gas and tangled magnetic fields stretching across hundreds of light years, a boundary so broad and so turbulent that material still fragments off it and drifts into the bubble's interior. Our immediate interstellar environment is not a random patch of space. It is the contested margin between two enormous expanding cavities, and the solar system wandered into it only a few million years ago. In a different direction, toward the constellation Orion, lies the Orion-Eridanus superbubble. This structure is considerably larger than the local bubble, extending roughly 1,200 light-years in its longest dimension, making it one of the more prominent features of our galactic neighborhood. It was carved and continues to be shaped by the ongoing stellar activity in the Orion OB1 Association, one of the most prolific star-forming regions in our part of the galaxy. The Orion Nebula, visible to the naked eye as a faint smudge of light below Orion's belt, sits within this superbubble, and it is not a relic from the past. New massive stars are being born inside the nebula right now, in this decade, and when they eventually exhaust their fuel and die millions of years from now, their explosions will add still more energy to the Orion-Eridanus cavity, pushing its walls farther outward and reheating its interior once again. The superbubble is an ongoing construction project, continuously expanded and maintained by the cycle of stellar birth and death occurring within its boundaries. In still another direction, toward the southern constellation Vela, lies the Gum Nebula, a complex and ancient structure, roughly 1,500 light-years across, that dominates a large swath of the southern galactic sky. The Gum Nebula is thought to be an old supernova remnant, possibly combined with the expanding wind-blown bubble from a massive star that has grown to enormous size over millions of years. Its outer shell is now so large and diffuse that it blends gradually into the surrounding interstellar medium with no sharp boundary visible. Within the Gum Nebula sits the Vela supernova remnant, a much younger and more energetic structure created by a stellar explosion approximately 11,000 years ago. The Vela remnant is still actively expanding, its shockwaves still racing outward through the older, cooler material of its parent nebula. This is a cavity nested inside a larger and older cavity, a younger bubble growing within an older one, both created by the same fundamental process of massive stellar death, operating on dramatically different timescales. The eROSITA X-ray observations that revealed interstellar tunnels extending from the local bubble toward the constellations Centaurus and Canis Major suggest that our cavity is physically connected to at least some of these neighboring structures. The tunnel toward Centaurus may link the local bubble to the Loop I bubble or to cavities beyond it. The tunnel toward Canis Major may represent a corridor connecting to the Gum Nebula region. If these connections are confirmed by future observations with higher resolution and sensitivity, the local bubble is not an isolated pocket of hot gas sealed inside cold walls. It is a single chamber in a larger network of interconnected cavities, linked by corridors of hot plasma that thread through the cooler, denser interstellar material separating them. This picture of the galaxy's interstellar medium as a volume dominated by bubbles and cavities separated by thin walls and filaments of cold, dense gas was first proposed theoretically in the 1970s by astrophysicists Christopher McKee and Jeremiah Ostrika. Their model predicted that supernova explosions would dominate the energy budget of the interstellar medium, continuously carving new cavities, reheating existing ones, and maintaining a large fraction of the galaxy's gas volume at temperatures exceeding 1 million Kelvin. The model was bold and counterintuitive. It suggested that what most people think of as the emptiness between stars was not empty at all, but filled with superheated plasma, organized into an intricate foam of bubbles and shells, a galactic-scale froth created by billions of years of stellar explosions. The model was controversial at the time because direct observational evidence for this bubble-dominated structure was limited to a handful of known supernova remnants and the puzzling soft X-ray background. 5 decades later, observations from eROSAT, eROSITA, the Gaia spacecraft, and numerous ultraviolet and radio telescopes have confirmed McKee and Oestreicher's basic prediction in spectacular fashion. The interstellar medium of the Milky Way is a dynamic, 3-dimensional architecture of hot cavities, cold shells, warm cloudlets, and connecting tunnels, continuously reshaped by the ongoing cycle of stellar death and rebirth, operating across the entire galactic disk. The original theoretical framework has been refined and updated, but its central insight stands. The galaxy is not a smooth fog of gas with stars sprinkled through it. It is a structure defined by violence, shaped by explosions, and organized into a complex hierarchy of nested cavities that extends from scales of a few light years to scales of thousands. How much of the galaxy's volume is filled by these supernova-carved bubbles? Estimates vary depending on the assumptions used, but current models suggest that hot plasma at temperatures exceeding several 100,000 Kelvin fills between roughly 20 and 50% of the total volume of the Milky Way's disk. The cold, dense gas where stars form occupies only a tiny fraction of the total volume, perhaps 1 to 2%, but contains a disproportionate share of the total mass because it is so much denser. The warm, partially ionized medium, gas at temperatures of several thousand Kelvin, similar to the local interstellar cloud, fills much of the remaining space between the extremes. The galaxy is overwhelmingly composed of thin, hot gas punctuated by narrow walls and filaments of cold material. The solar system, sitting inside one particular hot cavity, immersed in one particular warm cloud, shielded by one particular magnetic bubble generated by one particular star, occupies a position that is typical of a large fraction of the galaxy's total volume. Most of the Milky Way, by volume, consists of supernova-heated cavities. We are not in an unusual environment. We are in the most common and prevalent type of environment the galaxy has to offer. But knowing that fact does not diminish the staggering scale of what surrounds us. It amplifies it. The local bubble is one of the smaller superbubbles in the Milky Way. Many are larger, some dramatically so. The Orion-Eridanus superbubble at 1200 light-years dwarfs our cavity. Other structures mapped at greater distances from the Sun extend across thousands of light-years. The galaxy contains superbubbles large enough that the local bubble itself could fit inside them comfortably, the way a bedroom fits inside a house. And every one of these cavities was carved by the same process. Massive stars living fast, burning through their nuclear fuel in a few million years, and detonating with enough force to reshape the interstellar medium across scales that dwarf the solar system by factors that break the capacity of human spatial reasoning. Now, consider the full hierarchy of scales, laid out in sequence, each one nesting inside the next. The familiar solar system, the region containing the Sun and its 8 planets, spans roughly 8 light hours from edge to edge. The heliosphere, the Sun's protective magnetic bubble, extends roughly 2 light days in its longest dimension. The local interstellar cloud, the small warm cloudlet the solar system is currently passing through, stretches approximately 30 light-years across. The local bubble, the supernova-carved cavity containing the cloud, the heliosphere, and the solar system, spans over 1,000 light-years. The Orion arm of the Milky Way, The spiral arm within which the local bubble sits as one small feature among many extends roughly 10,000 light-years in length. And the Milky Way galaxy itself, the rotating disk of several 100 billion stars within which all of these structures are embedded, spans roughly 100,000 light-years from rim to rim. Each step in this hierarchy dwarfs the one before it by a factor that would be absurd in any context humans normally encounter. The local bubble is more than 100,000 times wider than the heliosphere. The Milky Way is more than 100 times wider than the local bubble. And the solar system, the place that contains every landscape, every ocean, every mountain, every city, every person, every memory, and every experience that any human being has ever had, is so small relative to the bubble that contains it, that locating it on any reasonably scaled diagram would require magnification beyond the capability of any printing technology that exists. You would need to enlarge a map of the local bubble to the size of a concert hall before the solar system's planetary region became visible as a single dot on its surface. This is not an abstract mathematical exercise conducted for rhetorical effect. These are physical distances separating real structures that interact with each other through gravity, radiation, magnetic fields, and the flow of material across their boundaries. The interstellar wind flowing through the solar system right now originated in the local interstellar cloud, which was formed by the collision of two superbubbles, which were carved by supernovae from stars that were themselves born from gas, compressed by even earlier explosions, stretching back hundreds of millions of years. The iron-60 atoms found in Earth's deep-sea sediments were forged in a star that belonged to a stellar association whose sequential explosions shaped the very cavity in which the solar system now drifts. The chain of cause and effect connecting you to the local bubble is not metaphorical. It is physical, traceable, and written into the geological record of our own planet. The ordinary mental image of the solar system, the one taught in schools, depicted in documentaries, and carried in the minds of nearly every person on Earth, is not merely simplified for convenience. It is fundamentally misleading in a way that matters. It depicts the solar system as a self-contained island floating in a void. In reality, the solar system is a speck embedded inside a layered series of structures, each one vastly larger than the last. Each one shaped by forces that operate on scales and timescales, completely alien to human experience. The void is not a void. The emptiness is not empty. The darkness between the stars has temperature and density and velocity and history and structure. It has been sculpted by explosions that each released more energy than the sun will produce in its entire lifetime, and it reaches into the solar system itself, flowing between the planets, depositing radioactive atoms on the ocean floor, and occasionally collapsing the very shield that protects Earth from the wider galaxy. When you look up at the night sky and see the stars, you are looking through the interior of the local bubble. Every photon that reaches your eyes from a star more than a few light years away has travelled through this superheated cavity on its way to Earth. The soft X-ray glow that instruments detect from every direction in the sky is the thermal radiation of the plasma filling the bubble around you. The cosmic rays striking Earth's upper atmosphere at this very second have been modulated by the heliosphere's interaction with the local interstellar cloud pressing in from outside. Everything you observe about the universe beyond the solar system is filtered through the environment the solar system is embedded in. You cannot step outside the bubble to get an unobstructed view any more than you can step outside the atmosphere to see without its distorting effects. The bubble is your observational context, your environmental baseline, the medium through which all astronomical information must travel before it reaches you. And until the 1970s, nobody on Earth knew it existed. This is perhaps the most remarkable dimension of the entire story. The local bubble is not small, it is not subtle, it is not hidden by extreme distance or exotic physics. It is over 1,000 light-years across. It is filled with million-degree plasma. It was created by at least 15 supernova explosions. It contains the great majority of stars visible to the naked eye from Earth's surface. It is, in physical terms, one of the most prominent features of our entire galactic neighborhood. And yet it was invisible to human awareness for the entirety of human history until instruments detected a mysterious X-ray glow that took decades to properly explain. The reason for this invisibility is instructive. The local bubble is invisible not because it is faint, but because it is everywhere. When a phenomenon surrounds you uniformly in every direction, with no edges visible, no contrasting background to set it apart, and no variation to draw the eye, it becomes the baseline. It becomes the definition of normal. You do not see the air you breathe because it is transparent and omnipresent. You do not feel the atmospheric pressure bearing down on your body at roughly 14 pounds per square inch, because it pushes equally from all sides, and your body has evolved to expect it. You do not notice the magnetic field of the Earth threading through your cells, because you have no sensory apparatus designed to detect it. And you do not perceive the superheated cavity of plasma that encloses your entire stellar neighborhood because you have never experienced anything else. There is no outside to compare it to. There is no moment when you cross the bubble's boundary and feel the change. The bubble is simply the invisible container within which all of human experience has occurred, unnoticed, unnamed, and unsuspected for millennia. Consider what this means for the history of astronomy itself. When Galileo first pointed his telescope at the night sky in 1609 and observed the moons of Jupiter, he was looking through the local bubble. When Edwin Hubble proved in the 1920s that the fuzzy nebulae in the sky were actually entire galaxies beyond our own, every photon of evidence he gathered had travelled through the bubble's superheated interior. When the Hubble Space Telescope captured its famous deep field image, revealing thousands of galaxies in a tiny patch of apparently empty sky, every single photon in that image had passed through the local bubble on its way to the telescope's mirror. This means every telescope ever pointed at the sky was looking through the bubble without knowing it. And that realization rewrites the history of observation itself. For 4 centuries of telescopic astronomy, nobody realized it was there, because nobody had the instruments to detect a phenomenon that exists at X-ray wavelengths, invisible to every optical device ever built. The discovery of the local bubble belongs to a category of scientific revelation that is particularly humbling. It is not a discovery of something new and distant. It is a discovery of something old and immediate, something that has been present all along, surrounding us completely, influencing our observations, shaping our environment, and escaping detection solely because human senses evolved to perceive a narrow sliver of physical reality that does not include million-degree plasma at interstellar densities. We built telescopes that saw farther and farther into the universe without ever noticing the medium we were looking through. We mapped galaxies billions of light years away without knowing what filled the space within a few hundred light years of home. The local bubble is a reminder that the universe contains structures at every scale, and that the ones closest to us are sometimes the last to be found, precisely because proximity makes them invisible. This realization carries a deeper lesson about the limits of human perception and the nature of the cosmic environment. The human brain evolved to navigate a world of objects ranging in size from grains of sand to mountain ranges, at distances from arm's length to the visible horizon, over timescales from heartbeats to seasons. Nothing in this evolutionary history prepared us to perceive or intuit structures that span 1,000 light years, that persist for 14 million years, that are defined by temperatures of 1,000,000 degrees and densities of 1/100th of an atom per cubic centimetre. These quantities exist outside the range of any human sense. They can only be accessed through instruments, and even then, they require sustained intellectual effort to translate from raw data into a coherent picture of the world. The local bubble is real, but it is real in a way that the human mind must work actively to grasp, because every instinct we possess tells us that the space between the stars is empty and that the solar system floats alone. The science is not speculative. The evidence is not ambiguous. The local bubble is mapped in 3 dimensions using data from the Gaia spacecraft. Its temperature has been measured by eROSITA. Its origin has been reconstructed from the trajectories of young stars and confirmed by radioactive isotopes in Earth's crust and oceans. Its influence on the heliosphere has been documented by Voyager, IBEX, and a generation of interstellar physics missions. Its role in driving nearby star formation has been established by one of the most comprehensive studies of the local interstellar medium ever published. The solar system is inside the local bubble. It has been inside it for millions of years, and the bubble is over 1,000 light-years wide. Everything humanity has ever known fits inside this structure. Every planet in the solar system, every moon, every asteroid, every comet, every spacecraft ever launched, every radio signal ever transmitted into space, every beam of light ever emitted by human technology. All of it exists within a cavity carved by the explosions of stars that died before our species evolved, before the genus Homo appeared in Africa, before the first stone tools were shaped by hands that were still learning what hands could do. The walls of that cavity are still expanding outward at this very moment, still pushing steadily into the surrounding interstellar medium, still collecting gas and dust along their leading edge. The stars forming on the bubble's surface are still igniting, still beginning lives that will last millions or billions of years. The tunnels connecting the bubble to neighbouring cavities are still being mapped for the first time by instruments that did not exist a decade ago. The story of the local bubble is not finished. It is still being written in X-ray photons collected by orbiting telescopes, in ultraviolet absorption lines measured toward distant stars, in the precise trajectories of young stellar groups tracked by the Gaia spacecraft, and in the radioactive dust that continues to settle invisibly, atom by atom, onto the floor of every ocean on Earth. You are inside it right now. You have always been inside it. Every generation of human beings that has ever existed has lived out its entire span within this one enormous cavity, and not one of them knew it was there. They built civilizations, they charted the stars, they launched spacecraft to the edge of the heliosphere, and through all of it, the local bubble surrounded them completely, invisibly, a structure larger than anything they had ever imagined sitting in the space between the stars, filled with the still cooling aftermath of explosions that reshaped 1,000 cubic light-years of the galaxy. The unsettling truth is not merely that the universe is vast. Everyone knows the universe is vast. That observation has been repeated so many times in popular science that it has lost its capacity to shock or to change how anyone thinks about their position in the cosmos. The real revelation is more specific, more personal, and far more disorienting. It is that even the solar system, the thing most people think of as their complete cosmic neighbourhood, their entire address in the universe, is not self-contained. It is not surrounded by nothing. It is embedded inside a particular environment with particular properties, an environment shaped by particular events at particular times, an environment that has left measurable physical evidence on the surface and in the deep geology of our own planet. The solar system does not exist in a void. It exists inside something. And that something is so much larger than the solar system that it reduces everything we have ever known, every planet, every moon, every human achievement, every signal we have ever sent into the darkness hoping someone might hear, to a scale so small it would vanish from any honest map of even our own galactic backyard. The solar system feels self-contained, only because human intuition is too small to perceive otherwise. We evolved to comprehend the scale of savannas, not superbubbles. We evolved to notice the things we can see and touch, not the million-degree plasma that glows in wavelengths our eyes were never designed to detect. The local bubble has been here for 14 million years. It will be here long after the solar system drifts through its interior and out the other side, long after the sun exhausts its fuel and dims, long after every trace of human civilization has been erased by time. It does not notice us. It does not respond to us. It simply contains us, the way a cathedral contains a single mote of dust drifting through its vast and silent interior. That is the picture the textbooks never showed you. That is the environment they never told you about. The darkness is not empty. The silence is not silence. The solar system is hidden inside something so much bigger. And now that you know, the night sky will never look quite the same again.